Hi, my name is Shehryar Sardar, and this is my Physics 2211 Lab 4 Oscillations. Here's my table of contents with introduction, models, experiment, code, discussion, and conclusion. The purpose of this lab is to observe an oscillation of an object handing on a spring moving in the x and y dimensions, and it's also to simulate the motion of an object handing on a spring and checking whether it follows the energy principle. Fundamental physics principles. Newton's first law, the law of inertia. An object at rest will stay at rest, and an object in motion will stay in motion unless affected by an outside force. An object moving experiencing no outside force will continue to move at a constant velocity. Newton's second law, acceleration of object is proportional to the net force it experiences, which simplifies to F equals ma. For our models, we have three equations. The spring force equation, which is negative the spring constant times the stretch times L hat, the direction of the spring, then velocity and position update. We have two more models, one for kinetic energy, which equals 1 half mv squared, one for gravitational potential, which is mgh, and one for spring potential, which is equal to 1 half kx squared, where x is the stretch or compression. Here is our results preview of the spring and the object over time, as the red object is the experiment and the blue is our model. And then on the left is our projected change in energies for K, U gravity, U spring, and total energy over time. Next up, the procedure. First, we need an object, a spring, and the earth, which is all part of our system. And we have no surroundings in this, and we need a camera to record. Step 1, measure the mass of the object. Step 2, stretch the object on the spring to some distance away from the equilibrium point. And step 3, record the object swinging on the spring. Next, we have our data collection via tracker. On the left, you can see images of the object on the spring at different positions, as well as its tracker points. And on the right is all the different points of its x and y, with x on the left and y on the right. Next, our initial values. The position we got straight from the first point on tracker. The velocity is 0 since we released the object from a still frame. Our initial time is 0, and our delta t is a really small number to make sure our measurements are accurate. And then our gravity, spring constant, L naught are all given to us, and then L hat, and S can be solved for, as well as the energy. Next is the loop. First off, we split F net into two forces, gravity and spring, which gravity is negative mg into y, and spring is negative ks times S times L hat. Then we update velocity and position with earlier models, and then lastly, we change the energy value to solve for delta energy. Next, our results. On the left, you can see the energy graphs, delta K, delta U spring, and delta E. Now on the right, you can see the position in the X and the Y. Red is our experiment, and blue is our model that we coded. Final results, as you can see in our X and Y positions, some similarities between the graph are similar periods and amplitude, yet a slight difference is how they're not exactly on top of each other. Some sources of error could be manual input, incorrect initial values, or poor coding, or inaccuracy due to coding not being completely realistic. Discussion questions. First, our energy principle. The normal energy principle is delta E is equal to external work. However, in our experiment, we had only systems and no surroundings, which means work is 0. And from our energy graphs, we can see that delta E was 0 the entire time. Second, our estimated oscillation periods in the X and Y, when solved, they were actually very close together, only off by 0.01 seconds, which makes sense because despite different forces acting on it at different times, like gravity, the oscillation rate of the spring would be the same no matter the direction. In the end, we experimented and simulated the motion of an object on a spring in the x and y directions. Thank you and have a good weekend.